Okay, so I would like to start by thanking Babak and Mark for the invitation. It certainly has been a great conference, and I've learned many different things. So the focus for us is targeted drug delivery. And let me start by explaining what is the basic idea behind targeted drug delivery. First of all, you start by designing a nanoparticle. Okay? And so this sphere here will be, the size of that sphere will be anything between 50 and 150 nanometers. As you can see here, it has empty space inside, and this is where we're going to encapsulate the therapeutic payload. That sphere, the composition of that sphere can be different. Okay? We can work with stealth liposomes, and this is the cartoon that I have here. The stealth liposomes are very natural, they are biodegradable, and they are non-toxic. They basically mimic a cell. They have been FDA approved, and this is a good model system. We can also design nanoparticles that the composition is 100% blockopolymers, and one such example is polymerosomes. Now, the focus for us is not how to design the nanoparticle. In fact, we can work with many different nanoparticles. The focus for us is the interface. How can I functionalize, or how can I decorate the surface of the nanoparticle so that it will do the right job? What do I need for that? I need two key components. The first one is the polymer, what I show you here. Okay? Why do I need the polymer? The polymer will give me a repulsion. We call this steric repulsion. That means that proteins from your blood will not adsorb on the surface of the nanoparticle. If they cannot adsorb on the surface, they cannot remove it from the flow. That means that the polymer is giving stealth properties to the nanoparticle. My body will not recognize it, and it will keep on circulating. And if I increase the circulation lifetime, that increases the chances of finding the cancer. The problem now with the polymer layer is that nothing can adhere to that layer. The nanoparticle is therefore cannot adhere to the cell and cannot internalize. How do I fix this problem? We can fix this by incorporating certain bullets. Okay? These bullets can be peptide bullets, can be antibodies, or can be aptamers. And aptamers are single-stranded DNA. In my group, we are focusing on designing peptide bullets, and this will be the subject of this presentation, but we are also designing aptamer bullets. Now, when I started discussing targeted drug delivery with different groups, the idea that many people have about the bullets is that the goal of the bullet is to guide the nanoparticle in the body so that I will go and find cancer. But this is not actually right. And in order to demonstrate what is the idea about targeted delivery and at what point are we going to use the peptide, I will show you this video. Okay. And I will mute this so that I can discuss what's going on here. So you start by injecting the solution that has the nanoparticles. Through the systemic circulation, they will circulate, and eventually they will go in the vicinity of the tumor. Now, the physiology of the tumor is very unique. There are blood vessels that are feeding the tumor, so you can see the blood cells and the white nanoparticles. And where the tumor is, the blood vessels have leaks. Okay? So the cells are not very close, and there are leaks. These leaks here have the size of 100 to 200 nanometers. And that's why we have to design the nanoparticles so small. So at the first stage, the nanoparticles will go in the vicinity of the tumor just because of the size. The peptide mostly has nothing to do with that. We call this passive targeting. Now, after the nanoparticles go to the vicinity of the tumor, they will mostly stay at the outside of the cell. The cell surface of the cancer cell will have many receptors or markers. These can be unique markers. If we design the nanoparticle to have these bullets, in that particular example they show antibodies, these bullets will bind to the marker. That will immediately cause internalization, as you're going to see. That binding of the bullet with the marker will allow the entry to the cell. And at that point, if you design the nanoparticle in the right way, you can release the therapeutic payload. Okay. So the goal for us is to design bullets, and in particular peptides, that will allow the nanoparticles to go inside the cell. And from that, we're going to get inspiration from nature. I'm going to discuss 3 different examples. The first one is viruses. Okay. Viruses are notorious for being able to deliver their cargo inside any cell. And so one way you can design such a peptide is a peptide that you can get from the HIV virus. If you are interested, we call this peptide TAT peptide. This is the sequence, and this is the kind of a peptide that we call cell-penetrating peptide. The problem with this peptide, like viruses, is that it can penetrate any cell, not only cancer cells. So I now face a challenge that if I decorate my nanoparticle with this peptide, it will internalize in every cell, because I'm not utilizing this specific interaction between the marker and the bullet. So Vladimir Tochilin came up with a very smart design where he engineered the nanoparticles. He had a very big polymer layer, so he basically was able to hide the TAT peptide. While the nanoparticle was circulating, the TAT peptide was inactive. It was hidden inside the polymer layer. But then when it came to the vicinity of the tumor has a lower pH compared to the rest of the body. And so these polymer chains here were conjugated to the nanoparticle with bonds that you can basically hydrolyze or break when they are exposed to low pH. So as soon as the nanoparticles came close to the tumor area, the pH was lower, the bonds were broken and hydrolyzed, and now the cell-penetrating peptide is exposed. It can do the job, and the nanoparticle can go inside the cancer cell. I am more excited about engineering the peptide itself. So how can we design the peptide and engineer this so that it mimics a protein, and we are after peptides that will give us a very specific interaction with the marker? So that you appreciate how specific this interaction is, I will basically compare this to a lock and a key interaction. For every lock, there's only one unique key that can open this lock. And so the goal for us is to design this peptide so that we'll have the right geometry, the appropriate sequence, so that we will get this specific interaction. The first brilliant engineering design of a peptide that mimics a protein came from the group of Matt Tyrrell. He was after designing a peptide that mimics collagen. And in particular, he wanted to target a receptor called CD44 receptor, and this marker is overexpressed in many tumors. So we knew that that particular receptor will bind to a particular sequence from collagen. We call this 4H1 peptide, and the sequence is there if you're interested. We also know that just this sequence is not enough. In order for us to get that specific lock and key interaction with the receptor, that peptide has to be in a triple helical form. So we need a secondary function, a protein-like structure. Unfortunately, when they synthesized the peptide and they evaluated the structure, they realized that you have absolutely no secondary structure. So how do you induce this? And they came up with the idea of conjugating the peptides to tails, hydrophobic tails, thus making this molecule an amphiphile. And then when 3 amphiphiles came together, they formed a triple helical structure. That was a brilliant engineering design. So they were able to get the specific interaction, and they demonstrated that when they functionalized nanoparticles with these peptides, they were able to target melanoma cells and deliver the cargo. In our case, we are interested in a slightly different challenge. We want to design peptides that have multi-domain binding. So how do we do this? One particular example is a peptide that will mimic a protein called fibronectin. This is a cartoon of the target over here. It's called alpha-5 beta-1 integrin. And this is a cartoon of the protein that we want to mimic. And this protein has many different applications, so we are not the only group that wants to design such a peptide. The first design, so this is part of the protein, not the whole protein. And we know that this protein has two domains that are extremely important, the red and the blue. And we know that the red and the blue has to be 3 to 4 nanometers apart. So the challenge for us is the following. How do I design a peptide that has two domains and they are 3 to 4 nanometers apart? If I ask you, you would probably say, you just choose any linker and that will do. This is what Cao and co-workers did. They used a polyglycine linker. Interesting to see that all the other papers after that, they also used polyglycine linkers. And the question for us is, are we done? Do we have a fibronectin mimetic peptide? To make a long story short, there were many different groups that started evaluating polyglycine peptides, and the answer is that the results showed that either the adhesion that we get between the peptide and the cell is kind of okay, but not spectacular, or if we try to use this for different applications, the results can be sometimes disappointing. So what was our hypothesis and the contribution to this area? We hypothesized that the linker is actually extremely important. How do you design this linker will influence the properties of the peptide. And we hypothesized that in addition to that distance, we also have to mimic the hydrophobicity and the hydrophilicity of that peptide. So we counted all the amino acids between the blue and the red. We realized that we have an equal number of amino acids, and so we designed a linker that is neutral, equal number of hydrophilic and hydrophobic amino acids. So now this is a peptide that has 4 building blocks: the red, the blue, the 2 domains, the linker, and a spacer. Now, how do you evaluate such a peptide? We don't just evaluate this peptide for targeted drug delivery. In fact, we do many different tests. I'm not even going to mention the different tests that we are doing. But the first test that we do is to evaluate whether we get the specific adhesion between the cells that express the marker and the peptide that we design. And what we show here, I'm not going to give you all the details, we evaluate cell adhesion, and we realize that, in fact, this peptide is doing a great job because it gives me the same level of adhesion compared to the actual protein that we want to mimic. We don't evaluate just cell adhesion, we evaluate cell signaling, we evaluate protein production, we evaluate cytoskeleton production, and this is just a beautiful image that shows you that when I have the cells on surfaces that are functionalized with peptide, these are not cancer cells. These are confocal images, so we can have a look of what's going on inside the cell. Basically, the organization of the cell is very strong. It's beautiful, it's well organized. That means that the cells love this peptide, and this is for a different application, tissue engineering, and they have to like this peptide. So after many different tests, we concluded that this is a peptide that is accurately mimicking the protein, and we can go ahead and use it for different applications. For targeted drug delivery, I can show you many different tests. I have a Peptides, I have my cancer cells, I design my nanoparticle. My nanoparticle, again, just to remind you, will be a liposome, for example. I will decorate this with a polymer, and I will include my bullets. Inside this nanoparticle, I can have fluorescent probes, I can have proteins, I can have genes. We start with in vitro evaluation, which means that I will start with my Petri dish and I will deliver the nanoparticles and I will evaluate adhesion, internalization, delivery efficiency. We've done this, we were satisfied with the results, and at the end we said, you know, that's not enough. We have to see what happens when we deliver this to an animal, because obviously things can be far more complicated. So that's the only slide that I will show you from our targeted drug delivery evaluation. So this is from a project that focuses on colorectal cancer that is metastatic. This is stage 4 cancer, the most difficult one to treat because it has metastasized in the liver. And this was the first time we evaluated the nanoparticles with animals. So we said, let's ask the most basic question. If I can evaluate different formulations, if I can vary the amount of the polymer that will give me the repulsion and the amount of the peptide that will give me the targeting, what is the best variation, what is the best formulation that will allow me to reach the tumor most efficiently? In order to answer this question, we also had to engineer the tumor or the cancer cells. And this is a very clever design that our collaborators did, where they engineered the cancer cells and they delivered a very special kind of DNA so that only when this DNA reaches the tumor, the nanoparticles go inside the cells, they deliver the DNA goes to the nucleus, it does the job, it produces a protein called luciferase, and then this is the signal that we detect. Simply because we can only detect the signal from the tumor, even if we reach healthy organs, we're not going to pick up any signal. Remember, the question is, which formulation will give me more delivery to the tumor? And for that, we decided to evaluate 9 different designs. The first row shows you nanoparticles that have a little bit of the polymer, but not enough. The second one, we increased that from 2% polymer to 5%. And the third one, we have a lot of the polymer, a lot of the repulsion, 10% of the bag. The first column shows no targeting, no peptide. Second one, 4% of my peptide. And then finally, 8% of the bullet. So what have we learned? If I have only a little bit of the polymer, it doesn't matter whether I have my peptide or not. All the nanoparticles go inside the tumor, and I see gene transfection. Okay? And that's because I don't have enough of the repulsion. So the nanoparticles will eventually go inside. But that also translates for me that most probably, if I can reach the tumor and internalize without the peptide, I can equally internalize in any other tissue. So that's probably not a good idea. The minute I start increasing the polymer and the repulsion, now we see that if I don't have the targeting, I don't have any delivery. The nanoparticles will probably go there just because of their size, but they will not get entry to the cell. They will not go inside. So then when I start incorporating the peptide, then we see a significant improvement. The other thing that we realized is that we can do this job with a tiny amount of DNA, 50 nanograms per milliliter. What does that mean for you? When our collaborators are basically just injecting naked DNA to the mice, they use 25 micrograms of milliliter, and that's basically 1,000 times more. When we gave them the nanoparticles and we said, we prepared the formulations and they have only 50 nanograms, they started laughing. They said, there's no way you're going to get any signal, forget this. We said, yeah, we have the ground, we might as well try this. So for them, it was impressive that you can do such a job with a tiny amount of the drug. And with that, I would like to conclude and summarize. And I think that I believe that targeted drug delivery is the future. I believe that it has many advantages. We can do the job using much less drug, DNA, proteins, chemotherapy agents. And we can do this in a specific way so that you can avoid the healthy tissues, and we can therefore have less side effects. And when it comes to the bullets that we can use, even though up to now people thought that antibodies will do the job, I think that peptides, and especially biomimetic peptides, peptides that you design to mimic a protein, are very promising bullets. And since I have discussed some of our work, I would like to basically thank the students and my group, because they are the ones that are doing the job, and more important, the collaborators, because as you might have guessed, this is truly an interdisciplinary project. So thank you so much.